Hello. I'll be describing a tool that we've been developing for about a year or so now. This was work done with a couple of really good undergraduate students that we had. John, he's in the audience right here, was one of the main developers, and another person, Mike, he's now gainfully employed. So what I'll be talking about today is very quickly going over what Flamingo is, what are the visualizations that we implement. As Bill alluded to, the data is complex. It has a lot of different things that you can talk about. So our approach to this is not to cram everything into a single display, but to do a series of displays, and then provide the user with the tools of toggling between these displays and toggling and selecting what information he wants to view in an effort to get at the information that they really want to extract from this raw data. Towards the end, I'll zip very quickly through some screenshots of some case studies that we've seen in our network since we've been using this tool, and we can always go into more details at the BOF, like Todd mentioned. So what is Flamingo? Flamingo tool enables you to navigate or explore your NetFlow data in a 3D visualization. It's OpenGL based, but it's also a real-time tool. So it has a 10-second interval over which it'll collect net flows and do some aggregation and then push the data out to the visualization client. That interval can be changed to be whatever you want it to be. So what we do is we provide a series of different visualizations. It's all based on NetFlow. We're not doing any external intelligence building on top of the NetFlow. It is what NetFlow contains. And then we add on the tools and the filters to let you select what information you're visualizing. Here's the architecture. It's a client-server architecture. You don't have to modify your NetFlow generators in any way. All you have to do is point them to export your NetFlow to the Flamingo server. The Flamingo server is then going to aggregate those NetFlow flows into BGP bins, prefix bins, and then export the aggregations out to the Flamingo clients. You can have multiple people connected to the same server. They can be looking at different views. They're completely decoupled from each other. Here's the different visualization methods that we use. Evan Cook at the University of Michigan mentioned the quad tree algorithm briefly yesterday at the NSPSec BOF. Some of you might not have been there, so I'll describe that briefly again. We implement 5 different views of the same traffic. We implement traffic volume by source and destination IP, traffic volume by AS. You can look at traffic distribution across ports, and of course, the final 2 are the most important that we found in our usage of this tool, which is flows between sources and destinations, and then traffic flows between source destination, source port, and destination IP and destination port. So here's the quad tree algorithm. What it basically does is it allows us to represent a 32-bit IP address into a fixed size space. What you do is, suppose you start off with a big square, you draw 2 lines divided into quadrants. What you can now do is you have 4 areas which you can represent by 2 bits, 2 binary bits. If you repeat this algorithm, as you see on the bottom right here, you can repeat the algorithm and now you can represent 4 bits. Repeat this 16 times and now you can represent a 32-bit IP address. So we apply that so this is a 2D mapping. What we now do is we take this 2-dimensional representation of an IP address, convert it into a 3-dimensional figure, and we have 1 axis of freedom, which we can now use to represent additional information in. So what do? In the first view that I'm going to talk about, this is the basic view. What we do is on the base of the cube, we represent the quad tree algorithm, we represent information from the BGP routing table, and then on the z-axis, what we can do is we can represent volume of traffic for each of those BGP prefixes. We use a different color for each prefix, and therefore you can see relative volumes of what traffic is in terms of source IPs or destination IPs that is being represented in the NetFlow records on your network. Here's what the figure looks like. This is a 10-second snapshot of traffic across one of our routers. The base of the cube is showing you the IP address space. Different colors are representing different prefixes. For example, this big purple bar over here is a /8. This blue bar over here is a /16. The volume is on the z-axis, and you can see volumes vary across prefixes. And I'll get into some of the filtering capabilities of this later on. I'll go through the visualizations first. The second visualization that I'll talk about is the source destination IP flows. Not only do we have just, so basically what we want to talk about, what we want to describe in this visualization is which sources are going to which destinations. So now what we have to do is we have to represent two 32-bit numbers. And the way we get around this problem is by using two surfaces of a cube and then representing the source on one surface, the destination on the other surface, and drawing lines between the source and the destination planes. The thickness of the line is scaled to represent the relative magnitude of the flow, so you can quickly identify which are the big flows and which are the small flows. And here's what that representation looks like. We have source IP addresses on the left. They're being aggregated by BGP prefixes. We have destination IP addresses on the right, again, by the same BGP table. And what we're doing is drawing lines between the source and the destination so you can see where your traffic is coming from and where it's going to. The last visualization that I want to talk about is how do we incorporate port level information in this, because NetFlow contains source and destination ports as well. What we do in this is slightly different than the two views that you've seen so far. In the first view, what you saw was the base of the cube was used to represent the IP address space, and then the z-axis, or the height, was used to represent volume. We only have one degree of freedom left, the z-axis. So what we do is we overload the meaning. In this visualization, we represent the port level information on the z-axis. Not volumes, but the port level information is on the z-axis. So what happens right now in this scenario is you end up with source IP source port that translates into x1, y1, and z1. That's 1 point in three-dimensional cube. And the same thing happens with the destination information. Destination IP, destination port translates once again to a point in three-dimensional space. Once we have this information, we can draw a line between a source and a destination, scale the width to be appropriate for the volume of the flow, and we can represent in a single comprehensive view a very accurate picture of what your current traffic as represented by NetFlow looks like. Here's an example of traffic for a 10-second interval. Once again, the port numbers are on the z-axis. We have source ports represented right here. Source IP source port is that point. Destination IP destination port is down here. And the same colors are used to represent traffic from a same source. So in this case, you can see that this source IP source port is sending out a large burst of data to various locations. Here's what the tool actually looks like. We combine the two-dimensional representation with the three-dimensional representation so that you're sort of oriented. Because the three-dimensional representation can be modified. You can rotate, you can turn, you can zoom in, you can zoom out. So you can often get lost where you are. So the two-dimensional representation sort of keeps you oriented in terms of what IP space you're looking at. We also have some additional windows that pop up. So, for example, there's a text representation of the information that you're visualizing. It provides you details as to what color is being mapped to what address, some description when we can look it up, what the frequency in terms of numbers is, sort of the same information we're using for the visualization, but in text form. More importantly, we have a bunch of slider bar controls as well. These slider bar controls are very important. What you can do with these is you can threshold what you're visualizing. For example, you can say, I only want to look at flows over certain volume. Or you can say, I only want to look at the first 1,000 destination ports. Or you can say, I only want to look at port 80 traffic. You also have the ability to enable and disable labels, which lets you identify points in your visualization. The last preferences box is very important right at the bottom there. What that lets you do, all the visualizations examples that I've shown you so far have focused on using the entire 32-bit address space. But a lot of people don't care. A lot of people don't care about the entire address space. They only have a /24 or /16. So what you can do is you can specify your source and your destination ranges that you're graphing or visualizing, and you can limit your view to only that size. I'll present this case study, which is one example that we came across recently, which proved to be very useful in illustrating how the visualization technique helps you extract information from raw data. So a traffic anomaly was reported on October 16th, and there was a large burst of traffic from one of the hosts at the University of Michigan. It lasted roughly 6 hours, and there was only a single source IP source port, but there were about 4 targets, not widely distributed. We could tell from using Flamingo that there were UDP flows, what ports they were going to, what those IP addresses were. And more importantly, what was interesting to note that this anomalous traffic was actually visible in your normal view. So when you just view traffic on a day-to-day basis using this visualization technique, you see a certain pattern that you see day to day. But when this anomaly happened, that changed, and that was identifiable using the visualization. Here's what that looked like. So what you're seeing over here is, once again, a 10-second snapshot of traffic going across the router. And all of a sudden, what you're seeing is a strange blue triangle right in the middle. Now, that's not normal. What this is representing is that there's a single source, and he's hitting a lot of destination ports at some destination. And this is a single source. You can tell that because he's using the same color. Now, that leads you to believe that maybe there's something interesting going on here. So now you look at the next view, which is you zoom in a little bit to focus your attention on where that traffic is coming from. In this visualization, what we're showing is the source volume from individual hosts, individual 32-bit hosts, from a /24 address space that we identified as originating the traffic. What we're seeing over here is the sheer large volume of the number of flows that a single host was generating, close to roughly 4 million flows in about 5-second time interval. And all the other flows, all the other hosts in the network are almost negligible in terms of traffic. So once again, illustrating very clearly that somebody is doing something strange. So now we go to the source and destination flows to see, well, we know there's a lot of traffic. Where's it coming from? Where's it going? This is where the source destination IP visualization helps us out. We can tell that we have a single unique source. His destinations are plotted clearly as 2 or 3 distinct targets in the destination plane, and we can spot the IP addresses very clearly. The lines are very thick, which means, once again, lots of volume. What about in terms of port information? This is the last view that I talked about. In this visualization, what you're able to see is the destination ports that are being targeted are essentially the entire port space. So you know that he's not targeting a single port, he's basically targeting entire ports. The information window right on the top of the screen is also showing you these are UDP flows, and these are the ports that are being used. So that's one specific example. Another example that we spot fairly often on our network is scans of different sort. For example, this is a representation of what a port 42 scan looks like. Once again, you can see the fan shape is essentially varying source ports, but they're all targeting into one point over here, which is one destination port. That is port 42. And this is sort of the signature visualization of a scan event. It's basically a source port varying, the target remaining the same. Here's what a network scan, this was actually fabricated. This was not observed. What we did was a scan of a /24 subnet, and here's what this looks like. It's a unique source on this side scanning individual hosts, and each one is showing up in a different color. This was actually something that I caught yesterday in our traffic, and I thought I'd include it in the presentation. This was an SSH scan. Once again, you can see it clearly in the visualization. It's the green fan-shaped entity over here, and it's using a lot of different source ports, but all targeting a single port. After you use the toolbars to limit and eliminate the external traffic, here's what the cleaned up image looks like. And this really illustrates the importance of being able to use those filtering tools. Another similar example is there was a /dot event on campus, and here's the relative volumes of what we saw during this event. Before images are on the left, after images or during images are on the right, you can see normal volume of traffic from a given subnet is very low. During the event, all of a sudden there's a sudden uptick in traffic, very drastic uptick in traffic, and that's traffic volume flow. In terms of the number of flows in source and destinations, you see roughly we see about 2 to 3 flows per minute, and then during the /dot event, an extremely large number. Here's an interesting representation of what scanning events, worm scans or propagation events look like. This is an example that we caught during the Zotop outbreak some time ago. We were able to identify an infected host, and then we plotted outgoing traffic from that infected host in terms of what were his infection attempts. Was it sequential, random? And what you're looking over here is essentially a random connection attempts. He's attempting to connect to random hosts because the destination is distributed fairly evenly across the 32-bit IP space. It's all originating from one source. That's why you end up with this cone shape. The cone shape is also illustrating because the source ports are higher and the destination target ports are essentially port 445. They're all the same. So it's basically attempting to connect to different random IP addresses, but all on the same destination port. And that's giving this cone shape visualization. This is the top view in this window over here of the same event. Here's some interesting traffic that we noticed, probably peer-to-peer. What it's showing you is basically a single host having all these multiple connections to a lot of different destinations with significant volumes of traffic to each one. And of course, you can apply the same thing to visualizing dark space traffic as well. And in this case, scans are very easy to spot. In fact, there's nothing but scans here. You can see blue scan there, the orange scan. You can, of course, using the drill down features, you can identify each and every one of those originating flows. But there's simply too much information. So that's roughly what the Flamingo visualization tool does. Once again, it's a real-time tool that can help you visualize your NetFlow data in an effort that you can actually get to the information that you're trying to get at. And that's it. They can be, if you guys are interested in more details, you can always show up at the BOF later today.
Indeed. Indeed. Yeah, and since we're running a little bit late and there's not a long queue of questioners, I'd encourage people who are interested in the details of Flamingo or ideas about how and why to process net flows in this way or for other purposes to show up at the Tools BOF this afternoon. I turn the closing of this morning's session over to our esteemed chair.